So, good morning, everybody. My name is Lauren Dominic Bolo-Dave. I am the project manager for the team Swarm, here accompanied by.
Hi, my name is Arrian Farahani. I'm one of the hardware leads for the team.
Hi, my name is Yenhung Chen. I'm working on the hardware side for this project.
Hi, my name is Douma, and I'm working on the software team.
Hi, my name is Reginald Capanzana. I'm also part of the software team.
So, we are here today to talk to you about a project that our advisor, Dr. J, presented to us.
So basically, unmanned ground vehicles are used for many applications such as path planning, object detection, and search and rescue. It is crucial to these applications that computational tasks are performed online. This means that results need to be computed and updated in real time, or at least as close to real time as possible. When a single UGV tries to take on these tasks alone, the time it takes to complete these tasks is extremely time extensive and much longer than real time. Because of this lag, oftentimes results end up being so outdated that they become expendable. Due to this reason, it is very inefficient and impractical for a UGV to complete such big tasks without help from additional nodes. So in order to enhance the computing performance of large computational tasks, the Swarm team has designed and implemented a distributed computing network. This network comprises of a master node and one or more other devices which also exhibit computing capabilities. The master node is able to offload parts of its computational load to these nearby computing devices to help distribute the workload. In doing so, the overall execution time will be diminished and therefore improve the overall performance. In order to demonstrate our distributed computing network, we will use an unmanned ground vehicle or UGV to act as our master node and a laptop as our additional computing device or worker node. These nodes are able to communicate between each other by sending and receiving data wirelessly. The task that our distributed computing network will be completing is the multiplication of two 240 by 240 matrices.
During Senior Design A in summer 2020, we envisioned a project that consisted of autonomous UGVs in a mesh network. The UGV's autonomous capabilities of object detection and object avoidance were to be enabled via camera. During the summer, our team spent the majority of the time simulating the autonomous capabilities of the UGVs via raw software. However, as fall and Senior Design B came around, we quickly realized that our project scope was vast and we had to scale it down if we wanted to finish on time. Thus, our goals during this fall semester was to build one UGV that was able to move forward and backwards via laptop controller, design a PCB to regulate power to all external hardware of the UGV, be able to control the UGV remotely, and simulate our distributed computing mesh network design with the UGV and laptop acting as master and worker nodes respectively. Here's our budget for a single UGV. One of our user requirements was to have the price of a single UGV to be less than $500. As you can see, the total price of one UGV totaled to around $300. Most of our budget was taken up by 3 of the off-the-shelf compute units on our UGV. Here are the 3 compute units that we used for this project. The Jetson Nano is a mini computer that has AI computing capabilities, and its main function for our project is to power the Arduino Uno and Zigbee 3 and run the Arduino IDE for compiling code. The Arduino Uno's main function of our project is to control the movement of the UGV via PID controls and motor drivers. The Arduino is connected to the PCB in order to control the motor drivers. The Zigbee 3 is an antenna connected to our PCB and is controlled via Python scripts on the Jetson Nano. The Zigbee 3 allows users to carry out high computational tasks like matrix multiplication. The hardware pictured here are the battery unit and the rover chassis. The chassis kit included 4 wheels and 4 motors, but it was our team's job to retrofit our fabricated PCB design, Jetson Nano, and Arduino onto the chassis. The battery we chose to power the UGV was chosen with the help of Mark Bruno from the lab. This battery is capable of powering our UGV for a full 15 minutes.
Awesome. Thanks for that, Reggie. So here I'm going to start talking about our block diagram of our system and our project and our PCB and circuit. So here, as you can see, this is our block diagram, which shows the flow of power and the general direction of our whole UGV system, similar to the circuit we designed. Starting from the left is our power supply, aka our battery, which powers our whole system. It powers the PCB, the Jetson Nano, which ultimately powers Arduino, the Zigbee 3, and so forth, and the rest of the passive electrical components. The Atmega 328P, which is our Arduino, controls the motor drivers, which finally ends at the motors for the movement of the UGV. Here you could see our schematic. The base of our circuit was designed based off the SparkFun L2 298 and motor driver, which is a circuit to control 2 motors. And ultimately we duplicated it to be able to control 4 motors total. The circuit runs through 3 voltage regulators. The first, which is a 5-volt regulator, drops down the voltage to control motor drivers shown at the bottom. The second 5-volt regulator drops down voltage to power the Jetson Nano, and then is also dropped down by another voltage regulator, the 3.3 volt one, to power the Zigbee 3. The circuit design was successful, and all the passive components were added based off hand calculations for particular voltage and current values needed for the circuit. Next came the PCB design, which was carried over to KiCad's PCB new editor for circuit tracing and component footprint editing. The green traces, which represent a top layer trace, and the red shows a bottom layer trace for your reference on the top right screen capture. Since the PCBs from Mark Bruno's lab aren't plated through, we had to add what is called a via to our PCB, which allows us to connect the top and bottom traces via a wire or a jumper cable. The mounting holes are also a reference ground and are connected to ground throughout the entire PCB. And finally, all components were soldered on correctly. There are also LEDs included on the PCB to verify that the board is powered and that all components are receiving power throughout the entire circuit. The L298HN motor drivers aren't included in the 3D view, but were soldered on later. Here we included a video which shows our PCB mounted in the rover chassis. As you can see, there are standoffs and screws holding the PCB in place. As well, on the top right are pictures to show our final product of the UGV with all the hardware mounted and connected. Each piece of hardware was mounted using non-conductive standoffs, which are secured to the rover chassis, and also the battery was zip tied to the chassis. I'm going to hand it over to Michael now for the rest of the presentation. Thank you. Michael, you're muted.
Michael, your mic.
Sorry. Here is the object detection simulation we have done. In this video, the object in the middle is a rover called Husky. It represents our own UGVs in the simulation. The model we use is YOLO for object detection. It is a real-time object detection system. It uses a lot of images as the inputs to train, and then use the output dataset to recognize the object in the video. The model is customized trained to recognize the Husky robot. It will detect where the robot is and label it with a number, which represents the accuracy of the detected robot. No matter the position, the size, and the angle of the object, the model will always detect and mark the object for us. Okay, the video in previous slide is the detection in simulation environment. Here are some pictures. These are the results of the detection in real world. Just like the video shows, the model has detected and labeled the rover with accuracy. These pictures show that the customized model a robot in different environments and the background. Also, multiple objects can be detected. These are the simulation tasks we did. We are looking forward to bring this into the real world implementation in the future.
All right, thanks for that, Michael. So just like as he said, these are all simulations of different functions if we were given more time that we could have implemented onto the rover. These two, flocking, are another example of an implementation that we could have done if we had more time. So flocking, showing you a video to the left, you can see that it's essentially a master node that we control. And the flocking is actually the autonomous movement of the given 3 different nodes right behind it. So as it moves, disregarding the one in the middle because it's Ross, as it moves, the 3 other nodes follow the master node, as well as trying to avoid each other for collision. So now the one I was showing you was without object detection. So the one on the right is the same implementation, but with object avoidance. So as you can see, here, when avoiding the object, you can notice that the flock does separate right here, but then rejoins the flock altogether. So that just showcased our autonomous movement, just in case we were going to implement it. Going to the next slide. These we have our final results. So the one on the right, you could see us using the laptop to connect via SSH to our rover. And then as you can see, we're now putting our Python script in order to move said rover via serial communication to our Arduino Uno. You can see 2 movements, 1 and 2. And now we're showcasing our matrix multiplication. So now this is with a sense of 2 nodes, essentially master and worker. As you can see right now, it's computing. I'm gonna skip ahead. At this point, you can see that the task has completed. From the results, you can see that the graph to your right, you can see that 1, this is the amount it takes to execute for 1 rover. But adding a second node decreases the time to execute that. So essentially adding more nodes to the mesh network, we can increase the performance of computing. Hence our summary of our events, starting off with 1.
We were able to create and control a working, moving UGV.
2, we were able to send data between computing devices wirelessly.
3, we demonstrated the time advantages of a distributed computing network.
4, we simulated additional applications beyond the physical scope of this project.
And that is the project for you, Dr. J, and thank you, Professor Dor.
And
special thanks
to Mark Bruno for helping us out in the Senior Design Lab, given the current situation of the pandemic. We truly appreciate it. And yeah, thanks for all your help. And thank you again, Professor Dor and Dr. J. All right.
Thank you.
Thank you.
Thank you.